what we've been doing is estimating slopes of tangent lines. And we didn't have a way of finding that slope exactly, so we made these tables of values. And we took x values bigger and smaller. So if I wanted the function near 2, you took x's that were smaller than 2 but getting closer to it, and looked at what your y was approaching, or we were doing slope, but we could talk about the y as well. Then you did the values bigger and looked at what they were approaching, and hopefully the 2 matched. So based on this, what would you say f of x was approaching? 4. It looks like both directions are getting closer to 4. In terms of a graph, we were looking at this function, and as you're traveling along this graph, as your x is getting closer to 2, my y value is getting closer to 4. And that's what's happening there. So this is what is called a limit. So the limit of the function f of x equals x squared minus x plus 2 as x approaches 2 is equal to 4. Notation, limit, and then underneath it this is small, x minus 2, like a subscript. Then we put our function here and what it equals. So this is saying as x gets closer to 2, this function is getting closer to 4. All right, and we could even verify that on this. Could you just plug a 2 into this equation and see what came out? Yeah. All right, so that is the actual, takes us into the actual definition of a limit, which says we can make our y value get as close as we want to the limit just by making x get closer to a. Okay, in the example we just did, I could make my function get closer to 4 just by making my x get closer to 2. And if I wanted to be getting even closer to 4, we would have to get even closer to 2. So the closer you get to the x, the closer your y goes to its limit value. That's the notation I will use. You could see it written like this. F of x approaches L as x approaches A. It's just saying y is getting closer to the limit as x is getting closer to some particular x value. So those all mean the same thing. Something that I really want to stress. A limit is not what happens that AC is blowing warm air.
That's why.
No, it's warm, but this one is blowing hot air, and I don't really know why. Turn it off for a while and see if it will recharge. Okay, a limit is not asking what happens at the point, just as you get closer to the point. Now for the graph that I was just looking at, it didn't really matter, but we can have situations where we might have an open circle at the point. And so the point itself is undefined, but we still have a limit because the limit doesn't care what happens there just as you get closer to it. So don't think that that point has to exist. For instance, all of these have the exact same limit. You notice this one's just a nice continuous graph. There's my limit. This one, when x is a, my point is down here, but the limit is still up here because I don't care what happens when I plug an a in, I care when it's approaching as you get closer to a. This one, at a, is undefined entirely, but again, the limit is still up here because I don't care what happens at the point, just as we get close to the point. So let's look at an example. I want to estimate the value of this limit. So the limit as x approaches 1 of x minus 1 over x squared minus 1. Can you just plug 1 into this equation? No. You get 0 on the bottom. So that will not work. I cannot just plug it in. So what do we do? Okay, how do we do that? What did you do on your homework for today? This time I'm not looking at the slope, I just want x and y. So it saves us a little bit. later on. But. So we need 2 tables, close to 1 that's smaller, so maybe 0.9, 0.99, 0.999. Close to 1 that's bigger, 1.1, 1.01, 1.00. And so then everybody grab a calculator. We're going to plug these in. So Logan, 0.9, Corbin, 0.99, Bell, 0.999, 1.1, 1.01, 1.001. Make sure you do parentheses around top and bottom. Let's do like 4 decimals. Logan, what'd you get?
0.5263.
Corbin?
0.5025.
Bell? 0.5. Bell?
0.4762.
Ben?
4975.
Bo? Okay. So what does it look like these are approaching? And they are the same, so we would estimate the value of this limit to be 0.5. Yeah, see? I did that on purpose.
You did that when you were gone.
How was that?
All right. How about, actually, here's what we're gonna do. Come to your property. Both parties.
I know.
When are we starting?
Now,
Wait, is it recording?
it is.
Oh.
So what do we do?
So since it's a part 2, 3, you need to get values that come close to 3. So you set up your so you get 2.9, 2.99, and values that come out are 0.387. 3,
And then since you're also doing on that side, you have to go above the 3. So do another chart. Excuse my penmanship, it's gonna be a whole lot worse than Logan's. So you have the values 3.1, 3.01, and 3.001, which then recommend come out to 0.4, 0.18, 0.4012, excuse me, and 2.4001, which then the common theme is going to go out instead of approaching 0.4. So our value is
Alright, very nice.
Go
Thank
team,
you,
go.
gentlemen.
we did it.
Alright, ladies, you are
Ouch,
up.
this hurts.
For real. It just wouldn't, right? It would be like,
Yeah.
mine would
There's a
either. I was
delay.
like, what the-
Okay.
It's lovely, it's lovely.
Alright, if you just hit the right arrow.
I don't understand.
And what would happen if they just plugged you in on this one, by the way?
It would.
Make
You would have just got to
Oh, not to.
I
was talking about mine.
Yes, yours. Yes,
That's 16.
I had to talk. I don't
you get to
understand.
talk. It's your chance to talk in my classroom, and I won't even yell at you.
We don't do that on the
I
radio.
know.
Do you want me to voice over?
Yeah.
Okay.
Yep.
So we're gonna set up a table here, and our first point is 1.9. Then we're gonna do 1.99, and then 1 point with 3 nines. And then when you put it in the little formula, you get 0.7959, and then 0.7996, and then you get 0.7 and then 3 nines. And then you gotta set up another table for the bigger than 2. So I did 2.1, 2.01, and 2.001, and that gave me 0.8039, 8004, and then 8000. And so they're both approaching 0.8.
Very nice. Thank you. Gentlemen, you are up.
Ben can do the right hand. I won't. I don't think Ben can. I just consider it. I don't know, but Ben said he'd do the right, so.
Ben might.
Hit the right arrow.
Okay.
Could you just plug in 0 on this, by the way? Probably not.
No, because then it'd be 0 on the bottom.
So once again, it doesn't even exist at 0.
Okay, so the first thing we do is we would make the two X and Y charts, where we decide to plug in negative 0.1 and negative 0.001, and negative 0.001. And on the other one, we went over and we plugged in 0.1, 0.01, and 0.001. And from those we got, on the first one, we got 0.1001. And on the next one we got 0.10001. We decided to just add more because otherwise it would have all looked exactly the same. And 1.00001. And then the other one we got 0.0999. And then 0.09999. And 0.099999. And we decided they were all leading up to 0.1.
So we should have a pretty good idea of what a limit is. Again, these are telling us that when our t is close to 0, the function is close to 0.1. Now, does that mean that if t equals 0, the function equals 0.1? No. This function is not defined at 0, so this is a very important point. It is not telling us what happens at 0, just when we get close to 0. All right. Let's take a look at this one. So we have what seems like a pretty solid method. If I wanted to do this one, we'd make our table. So negative 0.1, negative 0.01, negative 0.001. Before you put this in your calculator, make sure you are in radian mode. So then if we plug these in mode, and then make sure radian's high.
Oh, okay. Oh.
You're welcome. Alright, so if we plug these in, this one looks like it is approaching what? 1. And if we do the other table, we are going to get the same values because it would be a negative on top and negative on the bottom and turn out the same. So, I'm going to take this little time. So we can do it with trig functions too. What's the way we can kind of check if our answer was reasonable? Plug it in, like we could look at a graph. So if I were just checking to see if I want to graph sin x over x, and we can see that's our sine curve, and as we get closer to 0, the y value is getting closer to 1. So the graph can kind of confirm that. Is that okay? Alright, so let's do another one. I want to do the limit as x approaches 0 of sine pi over x. So pi over x, that's all in my angle. I'll put in the same values for the two tables. Okay, do we get the same when we put in the positives? Okay, so this tells me it's always 0. If I graph this, here's my graph. I'm going to zoom in. So here's when we're getting closer to 0. What's happening to my graph? Yeah. It's oscillating back and forth very, very quickly here. It actually turns out that this one does not exist. Hey, this is why I showed you that example. These tables can be misleading. They are allowing us to approximate. If I just went off these tables, I would have approximated 0. But what's actually occurring here is this graph is constantly bouncing back and forth, and it's not really approaching any single value. So we are going to get into better ways of approximating this, but I wanted to show you an example that kind of shows you the flaw in what we're doing. We're giving an approximation. It works great if we just have polynomials, rational functions, those kinds of things. Trig functions start to pose a problem. And there's some other uglier things where this method is not overly reliable. All right, let's look at this one. What kind of function is this?
Piecewise.
Piecewise. Yes, it's a piecewise function because we have pieces. Okay, so if I were to make my tables, if these x's are negative, which of these two pieces are you on? The bottom. Okay. So what am I going to get out every time? Negative 1. So if I put in any of these values, we get negative 1. So this side is approaching negative 1. This side, if we put in a positive, what do we get? 1. So this side is approaching positive 1. If we graph this function, you get 1 if x is greater than 0. Didn't we talk about graphing piecewise functions when we went through our review chapter? So the sum equal to is going to be an open circle. So this is just 1. When x is less than 0, we got negative. That's what the graph looks like. Your limit says I'm getting closer to 0. That means I'm coming in from both sides. What's the problem when I do that? They're not together. We get two different answers. So this limit does not exist because you get a different answer when you're coming in from the left and the right. So that leads us into the next piece, and we're going to do a little bit, try just a couple of examples with this today, and that'll be where we stop. We can do a one-sided limit. So these are two-sided. We look at both sides and see where they meet. A one-sided limit, I might choose to only come from the right or only from the left. If I had only approached 0 from the right, what would I have gotten? Positive 1. If I only approached 0 from the left, I would have gotten negative 1. So those one-sided limits exist, but two-sided did not. So let's look at this. If I ask you to find the limit as t approaches 0, so would this one exist? Think about the graph. If t is less than 0, you get out t. If it's greater than or equal to 0, you get out 1. So overall, if I'm coming from both sides, does this exist? Okay. The individual one sides exist, but if I came in from both at once, does it exist? No, because they're different. They don't match. So here, let me explain it this way. If I said the limit as t approaches 0 from, I'm going to put a little positive. That means from the positive side or from the right. So I'm coming from things bigger than 0. So if I'm traveling from things bigger than 0, what does this approach? 1, 0. As my t or my x is getting close to 0, the whole thing is getting close to 1. As I approach it from the left, what's it approach? 0. So these left and right limits exist, but the overall two-sided limit does not because these numbers are different. Okay, in order for the two-sided limit to exist, the left and the right hand have to be the same number. Does that make sense? So that's actually what the next box has. Just spells that out in words. That in order to have a two-sided limit, the left and the right have to be equal to the same number. I want to do the last two more examples, examples 5 and 6. equals 1 if x is not 0. What's that look like? So when x is 0, we get an open circle, and everywhere else is 1, so this is horizontal line. 0 if x equals 0, what's that? What's that? So what's the limit as x approaches 0 from the right? So if I'm coming in with things bigger, it's going to 1. As you approach 0 from the left, what y value are we getting close to? This line is still at 1. So these match. So that means the overall two-sided limit exists. And it is 1, which we could have seen from the graph. If we come in from both sides, my fingers meet. They meet up. So we do have a two-sided limit. We're going to try another one just looking at a graph and kind of trying to understand what this is telling us, and then we'll pick up with it tomorrow. Okay? So, here's a graph, and I'm going to find each of these things. First one. The limit as x approaches 2 from the left. So I'm coming in from the left. As my x is getting closer to 2, what did my y value get close to? As we approach 2 from the right. So as I'm coming in from this positive side, I'm getting closer to 2, what y value do we get close to? 1. So, what's the two-sided limit? If I do left and right at the same time? It does not exist. These numbers aren't the same, so the two-sided does not exist. So the limit as we approach 5 from the left. So I'm coming in smaller than 5. What y value are we getting close to? What about as we approach 5 from the right? 2. So what's the two-sided limit at 5? 2. Because those match, we've got a two-sided limit. Questions there? That's our stopping point for today. We have a handout for you. Got 10 minutes or so to work on it.
No, that was, I'm reading Frankenstein, that's at home.
This is not a book you are choosing to read on your own.
If you turn it around, it's the little pad.
Oh, yeah, you're not shooting to read it, what's it for? That's rough for you, huh?
Next is the Odyssey.
Yeah, yeah.
And then after that,
And I think classic literature, I had to show it.
no, I would